Hi, hello, namaste. Now, in the previous video, we worked with reflection coefficient where we had a step potential and we basically made an incoming wave pass through it as transmitted through it. And when we did it, we had this equation which we worked with where our energy was less than V naught. Now we work with another form which is transmission. Well, in the previous video, if you could see the reflection coefficient, the particle did get transmitted, but it was in such a way that energy was less than the potential, so it had to decay. So it got decayed, and at some point it became absolutely zero. Now in this following, we basically will work with energy which is being greater than our potential wall. So with that, we begin with our lecture of transmission coefficient, where the decay, of course, as I told you, that decay appears when our E is less than V. So now that we can work on this, we will further continue to make our or form our equation according to the incoming and the transmitted equations. So of course, there is this one wave which is the incoming wave given by a e raised to I k x, and when it reaches that point, it gets reflected back with the equation b e raised to minus I k x. The negative sign indicates that the reflection is on the opposite side of the incoming wave. Now, as some of the particles, as some gets reflected, some gets transmitted in, and this transmission we will refer to as f e raised to I q x. And we call this region to the left as region 1 and this region to the right as region 2. So region 1 and region 2. Now we consider the following equations for specific regions. So in region 1, where our x is less than 0, we have this equation of psi 1, the wave function, as a e raised to I k x plus b e raised to minus I k x, where our k is basically root 2 m e by h cut square. This comes from Schrodinger's equation. And in region 2, where our x is greater than 0, we have the psi 2 given by f e raised to I q x, where my q is basically root 2m e minus v naught upon h cut square. This too comes from Schrodinger's equation, but where in this region we consider the value of v naught in the equation itself, and that's how we get this. Now after this we apply the boundary conditions, which is basically at x is equals to 0. So apply boundary condition at x is equals to 0. So therefore we get the continuity equation, continuity of psi, we get continuity of psi as in the form a plus b is equals to f, because we are considering the whole system now, because that is what it means. Continuity of psi is basically, we're not separating it with psi 1 or psi 2, but we are considering the whole system, so we write in the combination of it. Now we take the derivative of it, so we'll put that continuity equation derivative as d psi by dx. This is equation 1, by the way, and when we take the derivative of this, we get ik a minus ikb is equals to iqf. If we give this equation 2, now from equation 1 we insert, of course let me just write the equation 1, f is equals to a plus b. In this equation we insert the value of equation 2, and we basically write that insert 2. Therefore our equation becomes iqf is equals to Ka minus I Kb. We got this equation. We can just eliminate I because it is common. So we can just write that Qf is equals to Ka minus Kb. Since F basically means A plus B, we can put the value of F in this. So Qa plus B is equals to Ka minus Kb, and we multiply Q inside. So Qa plus Qb is equals to Ka minus Kb. And further, now we'll write this as, we can just take this on that side and this on this side. So this becomes Qb plus Kb is equals to Ka minus Qa, which we can write we can take B as common and A as common. So we get B Q plus K, and our A is common, so K minus Q. Perfect. Now from this we can just construct the further equation. We can say B upon A is K minus Q and K plus Q. So we got this equation now. We move to the next step, that we will again consider equation 1. So let's say from equation 1 we can construct something like this. F is equals to A plus B, where we can take A common. If we take A common, it becomes 1 plus B upon A, and we have already constructed B upon A here, so we'll just put it inside. A, we can take A in the denominator, that becomes easy, and 1 plus K minus Q, K plus Q, and we can just cross multiply this, and it becomes F upon A is equals to K plus Q plus K minus Q, and it becomes K plus Q. Since Q is like with different signs, and it will get cancelled, and F by A becomes 2K upon K plus Q. This becomes our F upon A. Since we got this as F upon A is equals to 2K upon K plus Q, we can construct our transmission coefficients equation, which is given by T is equals to J transmission upon J incoming, which is Q upon K and F upon A the whole square. Well, you may ask where this Q upon K came from. It came from the probability current density. As we know that equation, I'll just write it in brief. Probability current density, which is given by h cut upon m Im psi star d psi by dx. Psi star d psi by dx. So since we have Q and K, so our equation kind of becomes for J, it becomes something like h cut Q upon m and f square, and the other one is like h cut K upon m with a square. So like if we just divide it, we get this gets cancelled, and we get our equation as this. So the transmission and the incoming both are like given in this form. This was just a brief explanation to how this came in picture. Of course, since we got F upon A, we'll just insert this value inside this. So our transmission equation becomes Q upon K, and this goes here. 2K is equals to, 2K upon K plus Q raised to square. So T is equals to QK, and you just square it, 4K square and K plus Q the whole square. Now K to K gets cancelled, so one of the numerators K gets cancelled with the one of the denominator. So 4kq, as one k is left from numerator, so 4kq and k plus q the whole square. So this becomes our transmission coefficient. Now if we want to verify that whether the reflection and coefficient equations are correct, we will basically just check it. We will take the addition of both. So t plus r is equals to this, we put of course here, but where is r? So in the previous lecture we had and we got r, and it was something like this, which is r is equals to k minus q, k plus q. Now just one thing is that I took different notation in the previous lecture. So this is how our r came. This is what our r came. This is our t already. So we will just put these two equations inside this, and we get something like 4kq plus k minus q the whole square and k plus q the whole square. Since both the denominators are same, so we can just write it at once in, and then 4kq plus k square minus 2kq plus q square. We simply expand this, and we also expand this, 2kq plus q square. So if you just expand and you get this 2kq, and here it is 4kq in positive, so we get positive 2kq, right? So k square plus 2kq plus q square and k square plus 2kq plus q square, which becomes 1. So t plus r, it becomes 1. And what does this concludes to is that this relation that t plus r is equals to 1 expresses conservation of probability current, which means either the particle is reflected or transmitted. Thank you so much for watching.